So here I'm showing with the two criteria, fixed threshold or fixed number of links for constructing the network. What are the t-values of these statistics when we separate the groups in three groups with small inferior parietal thickness, middle or large. And as you see, all values are between, let's say, -3 and 3. So we can say there is no relationship. Okay? But if we study one of the variables, that is the amount of sleep, we see that the t-values now take values like -7. That is, that this shows that there is an important relationship, or that the central networks are really different in both groups.
The amount of sleep when?
Okay. The question basically is, in the last month, in average, how much you have sleep. And if you study another variable, that this is let's say a brain volumetric variable, what is the middle temporal area, we found the same. There is some technical point here that the test, the ANOVA test, is think for one value. For when you have three sample of networks, but for where there is no dependence. When you are moving the correlation threshold, you are imposing a dependence in the networks. Network with a correlation, let's say, greater than 0.5 will be similar to 0.15. So that's why we have to make some bootstrap in order to be sure that the results are robust. So basically, the idea is we separate in positive networks, negative networks. Negative, this is if the correlation is smaller than some negative value. And we measure how many points are in this region, in this, and this, and we take the minimum. Okay? So in this case, we have 10, 10, 9, 9, so W3 is 9. In the case of inferior parietal thickness, you have always 0. And now we do bootstrap, we try to understand how is the distribution of W3 under the hypothesis that there is no relationship. When we do that, we observe that almost all have W3 0, some 1, and the others nothing. And so what I want to show is that basically we have strong evidence that at least the amount of sleep and middle temporal area are important. This is the identification problem. Yes, we have to find in this large space, but in the space of nodes, because the space of links is impossible. Okay, so very quickly, we found many other variables, behavioral variables, brain volumetric variables. These brain volumetric variables are correlated. So one important thing is in neuroimaging is, humans are highly variable in their brain activity, which can be influenced by their level of alertness, mood, motivation, health, and many other factors. Even the amount of coffee drank prior to the scan can greatly influence resting neural activity. This we put, it was funny because we put this in the paper and we have any evidence, and 1 week later appeared this paper. So I think in some point many of the neuroimaging data can be very influenced by strange factors as, are you waiting? In 5 minutes we have a scan, take a coffee, and perhaps we are observing this type of things. And another important thing is that we identified as relevant many brain volumetric variables, and these volumetric variables you know only when the people is in the scanner. So in order to compare, to first have a huge number of subjects, then they say, okay, they have the same volumetric variables, they have the same test, they haven't drank coffee, they have sleep the same, and then you can, okay, is illness or not different in this subject? So finally, based on just distance, we have robust statistical comparison. As you imagine, there are many applications. Take care of confounding variables. And recently, our package that is called StatGraph has been developed by Josan Santos and Eduardo Lira, Andrés Fujita from the University of São Paulo, and some of the things, in particular, ANOVA test is here. So if you are interested, you can download.
Very nice way of comparing graphs, and I haven't seen anything like this before, so I will use it. But two questions. One is, if you take the same data set that you just showed us and use one of the traditional cluster coefficient or clustering coefficient in order to separate or degree distribution or some other of the things that typically people measure, would you have something similar? And the second question is, do you have to do multiple testing corrections because you are checking different rows or different ends? Yeah.
Okay. Our method is more sensitive than to the research think that this variable will be the sensitive, because in this distance you are considering all the relevant things. For example, in the clustering coefficient, but why this can be relevant, and so in this way is the I think it's the most sensitive case. For example, I will show just one naive test. One naive test for networks could be, okay, I will say that both central graphs are different if at least one link of many is different, okay? So in this case, we modify some of the links to compare that. This is the performance, the power, the sensitivity of the test when you have, let's say, small difference between some links here, and all the same are the same. And when you put this naive test, obviously corrected by multiple comparison, you obtain something like this. So it's much better than what could be a naive test. And the other question was?
Well, you just responded because you used Benjamin Hochberg correction.
I used Benjamin to compare the network test, the ANOVA, to a naive test. There is no standard network test.
No, I was saying, but if you do something like that, when you, in a way, you are taking the minimum over all rows.
Yeah.
And that somehow you are testing many times, right? And
yes, that's why we use Bootstrap, because we don't know the distribution when there is that evidence. Yeah.
Any other question?
Just a simple one. What about weighted network? So how can you improve the weight?
Okay. The idea was, you are working with networks, so stay in your space. And the central network is in the space. Now, if you see with here, I don't put C. In the original version, use the central graph here. Here is the average network. But why we use the average network? Because we have more sensitivity. In a test, what you want, the most sensitivity you can. So,
The average is the average over all the weights? Or
yes, is the average, is exactly.
And then you say 1 or 0 depending on because you...
This M is just, let's say, if this link is present in 3 of 10, will be 0.3 in this matrix.
So this value may be fully
is-
connected.
Yeah, sure. Yeah.
The only thing you need is a distance between network. But
Exactly.
it could be weighted, fully connected, whatever.
Yeah.
You just give a distance and that's it.
Yeah, but this is the same. We have the same result if I put here the central graph, not the average.
Okay.
That is,
But I don't understand because
Yes.
the distance is the edit distance, right? We're talking about the edit distance, right?
Yeah.
So that requires that you have or don't have is binary. So you have to always say if the
Okay.
average is less than 0.5 is 0.
no. Okay, this was like for simplifying. For networks, we all the first talk we always use the edit distance. Now, here, this I can put the distance and the central graph, and it's the same. Now, if I want a little more of power here, let's say if I put in this, if I put the central graph and the distance, this power will be something like this and like this. So in order to gain sensitivity and put more power, I just put the distance, but now is like one link is 1 minus 0.3, not 1 minus 1 or 1 minus 0, but it's the same.
Yeah, I understand.
No one else? Okay, then, thank you very much. That's it for the day.